Okay, guys, just find my window here. Okay, so yesterday we talked about indicators, and today we are going to just continue on with that. Just a few quick example questions dealing with the Ka of an indicator and just various color changes. So it won't be as long as yesterday, but I thought I should probably go over a couple questions just to review some things here. So let me just share my screen. I hope you guys are doing well today. I haven't really looked outside. It looked kind of sunny this morning, but I'd hope to go for a ride, but I don't think that's going to happen. Switch, yes. And I turn my video off. Go away. There we go. Okay, so let's take a look at an indicator like, let me see if I can find one here. I have my data table with me. So let's try alizarin yellow. That's always a cool name. Alizarin yellow. And just to start off, I'd like you to determine the Ka of this acid. So remember, indicators are weak acids in conjunction with their weak bases. And the question is, what is the Ka value here? Okay, so what would the Ka value be? Okay, so I'll let you work on that, and I'll just write out the equilibrium here for it. So okay, so alizarin yellow has a pH color range from 10.1 to 12.0. So 10.1 to 12.0. And that means if it's below 10.1, it'll be a specific color. And if it's above 12.0, it'll be a different color. And according to the data table, it should go from yellow to red. So yellow to red. So if we were to have this indicator in a glass of water, the water being pH 7, it should be yellow. The solution should be yellow in color. If you added it to some hydrochloric acid, it should be yellow in color. And if you were to add it to a base of a fairly high pH value, so like around 13, then it would definitely be red. And if it was somewhere between there, let's say you had a pH of like 11, so it wasn't below 10, it wasn't above 12, then it would be a blending of those colors because you would have roughly equal amounts of the color together, and you would have like an orangey type of solution then. Okay, so we talked about that already. And so what I wanted to go back to and just to review, because I think it really is important when we start talking about buffers, is this idea of V half. So I just did a real quick sketch of a titration curve involving a weak acid, which is what alizarin yellow would be, and titrating it with a strong base like KOH or something. And so we would see this little blip at the beginning here. This is pH on this axis. This would be the volume of the base being added. And so we see this real gradual range here where the pH doesn't seem to change very much. And right in the middle of that, we're going to call that V half. So that V half indicates it's half of the V value, which means half of the volume required to neutralize all of the acid. So if you neutralize half of the acid, then you would have half of it. And if you neutralize half of the acid, you should have an equal amount of conjugate base forming here. So when we're at V half, so when we actually get to V half, the concentration of the acid, so the concentration of H Ali, should equal the concentration of Ali minus. And once again, this becomes very important when we talk about buffers and how buffers actually work. So what that would mean is that if we're at V half, then the Ka value at V half would equal to, well, if the acid and the base are the same concentration, then we would just have the concentration of the hydronium ion when we are at V half. But remember, V half is here on the graph. V would be at the equivalence point. But it doesn't really matter where you are on the graph. The K is a constant number. K is a constant for that acid at that temperature. So, so how could we use that? Well, we could look for the pKa for the indicator. I didn't use that word yesterday. We could look for pKa first. And if we think about that, the Ka would have to be something to do with the hydronium concentration, which would have to do something with these numbers here. So let's find out where it would be at V half. That is, where does this hold true? And that would be at the middle of the color change, or we sometimes call it the end point of the indicator or the transition point. So if we take 10.1 and we add it to 12.0, and we divide it by 2, so we're going to take the average of these numbers. So 10.1 plus 12 divided by 2 gives us a pH measurement of 11.05. So that would be the average of those two numbers. But more importantly, that would be the pH where you're in between the transition of the two chemicals. So basically, you would have equal amounts of H Ali and equal amounts of Ali minus. So you would have that. You'd be at V half. So you're at V half when the pH is this number. Okay, so the pKa would be the negative log of the Ka, if that makes sense. So negative log of the Ka value. Okay, so in order to find the hydronium concentration, we would take the antilog of that. So we would say the Ka value at V half would equal 10 to the negative pH. So 10 to the negative 11.05. Now, of course, Ka at V half is the same as Ka at V 1/5 or Ka at V nothing. K is just constant. So we'll go 10 raised to the negative 11.05, and we get a value of about 8.9 multiplied by 10 to the minus 12. Okay, so that's a fairly weak acid then. That's fairly weak there. Okay, so just a quick review of a question we did yesterday. And let's give you now a specific question dealing with, I lost my page. That's brilliant. Well, there we go. Okay, so where is it here? So yeah, so let's take a look at let's say you had solution here. So we're going to have so let's say you had a solution where the first one was 0.1 molar HCl. Okay, so 0.1 molar HCl. And then you had another solution that was 0.1 molar HF. Another solution that was 0.1 molar H2CO3, and another solution that was 0.1 molar NH4 Cl. There's 4 solutions here, okay? And just need to do one small thing here. Sorry about that, guys. So we go back to this slide here. So we have these 4 acids, all the same concentration, and different chemicals, of course. And let's say you had a bottle full of one of these chemicals. Okay, so you just don't know which chemical it is, but it does belong to one of these groups here. So it could be up on a chem shelf where you got all these chemicals labeled, and all of a sudden you have this bottle is unlabeled, but you know it's one of the following chemicals here. And so you take a sample of it. So you take a sample and you test it. So you run a little test. Maybe you use multiple samples here. So you just put a little bit in the bottom. Okay, so you do 3 samples. And what you're trying to determine is which chemical it is here. And so in beaker A, beaker A, beaker B, and beaker C, you use 3 different indicators to sort of narrow down what it could be here. So in beaker A, we're going to use methyl violet. And in beaker B, we're going to use methyl orange. And in beaker C, we're going to use phenol red. Okay, and then obviously we look to see what color would pop out here, and what we would based on that we try to make a determination on which chemical it would be here. So let's say that with methyl violet we test it and it turns out it's blue. Okay, so you get a blue color with methyl violet, and then with methyl orange we get orange. So you get an orange color when you use methyl orange. And with phenol red, we get a yellow color. Okay, so it turns yellow. So we get these 3 different color changes, and based on that, we're trying to determine what chemical is actually in this beaker here. So let's determine the range that the indicator would have to be here. So according to methyl violet, if you are blue, your pH must be bigger than 1.6. So it must be bigger than 1.6. And if you are methyl orange, then you should be, well, you're either methyl orange, you're either red if you're below 3.2, and you're yellow if you're above 4.4. So 3.2. So don't forget you're yellow. You're yellow if you're below that. And you are methyl orange. No, you're red. Yellow on this side. Yellow. Okay. And you would be red if you're on this side. So the fact that it's orange would mean it's somewhere between those numbers, actually. So we're somewhere between those numbers. And then phenol red, I don't know if that's going to help us now because we kind of got a narrow window here. Phenol red would be yellow if it's less than 6.6, which is kind of not that important, really. So we know that it should be between 3.2 and 4.4, I guess. So let's see if we can narrow this down a little bit better here. Okay, so if you're talking about the various acids here, you'd have to know their strengths. And so we've got a strong acid with the HCl. That's our strong acid. And so I would just negative log that number to determine the pH. So the pH here would have to be 1. Let's not worry about sig figs here, just trying to get a ballpark number here. So if I negative log 0.1, so negative log of 0.1, I get 1. Okay, so that is quite low. So this bottle, whatever it is, cannot possibly be hydrochloric acid because first of all, methyl violet should not have been blue. It would have been probably in a yellowy blue kind of color, kind of a greeny kind of color. Okay, so we know that it's not that. Okay, and then the other chemicals, HF, that's a weak acid, so that's possible its pH is there. H2CO3 is a weak acid, so that's there. But what about this NH4Cl business? Well, if you go back to the last chapter, NH4Cl is a salt, and since it's molar, it means it's in solution, which means you have ammonium ions and you have chloride ions. So ammonium ions are acidic, and chloride ions are neutral in water. So this actually would be an acidic salt. So all three of these would actually act as weak acids. So I'm going to just write up a general equation for a weak acid in water. And so the HA here could be any three of those. So you would get the conjugate base forming, and you would get your hydronium. And you have your initial, your change, and your equilibrium conditions. And so every one of these starts at 0.1 molar. You have 0, 0. You'd be going to x's. So plus x, not sure why I put plus signs down there. And then it would be minus x over here, 0.1 minus x. And so the Ka of this would be the concentration of the base multiplied by the hydronium all over the concentration of the weak acid, whatever acid you want to look at here. And really, if I use my assumption statement, I would get x times x is x squared, and I'll assume the ionization is quite low, so hopefully I did this correctly. And then what I'd want to do is work out, I guess, the concentration for x of the various chemicals. So for HF, this would be 3.5 times 10 to the minus 4. And for H2CO3, so H2, let's go down a bit here, H2CO3, it would be really the same equation, x squared over 0.1 equaling, where is it here? I think it's 4.3 times 10 to the minus 7. And then I'll do NH4 plus, and that would be x squared over 0.1 equaling 5.6 times 10 to the minus 10 here. Okay, so I'll kind of do these as separate calculations. I'm going to do most of it on my calculators. Hopefully you guys can kind of follow along here. So I'm going to go for the HF here. I'm going to go so 3.5 times 10 to the minus 4 multiplied by 0.1. And then I square root that number. So I square root that number, and I get x, which is the hydronium concentration, which is equal to 5.9 and change times 10 to the minus 3. And then I negative log that number, negative log, and I get 2.3 approximately. So I get a pH equal to 2.3. Okay, if I do the same thing for carbonic acid, I would get an X value, which is a hydronium concentration equal to, let's do that, 4.3 times 10 to the minus 7, times it by 0.1, take the square root, and that's not right. 4.3 times 10 to the minus 7, times it by 0.1, take the square root. So I'm getting 2.1 roughly times 10 to the minus 4. I'm going to keep the number on my calculator, which you guys can't see, so just maybe hopefully believe in me. And so I'm going to find the pH of that, so I negative log that number, and I get a pH of about 3.7, roughly. And for the last one, for the ammonia, 5.6 times 10 to the minus 10, and now times that by 0.1, and then take the square root, and I get an X value, which is the hydronium concentration for the NH4, equal to about 7.5 times 10 to the minus 6. And if I take the pH of that, which is the negative log, I get a pH value of 5.1 roughly. Okay, so once again, these aren't worrying too much about sig figs here, just trying to see if I get a ballpark number. So let's just shrink that down a bit. So this pH here is 2.3. The pH here was 3.7, and the pH here was about 5.1. These are kind of approximations number here. Okay, so let's see if we can narrow this down now. So we know the pH, we said before, has to be between those two numbers. So it has to be more than 3.2, but less than 4.4. So with these three indicators, which have fairly wide ranges to narrow down the numbers, I think we can definitely determine that a pH of 3.3, so this one, 3.7, sorry, would definitely fit in between those numbers. And so the pH giving us 3.2 to 4.4 for the methyl orange would be orange. Sort of helps us know the bottle actually is carbonic acid. So this bottle here would actually have to be H2CO3. Okay, so there's a little bit of overlap between the previous chapter where you can determine pHs of chemicals with weak acids and weak bases, Ka and Kb values, and of course strong acids and strong bases too. So I think I'm going to stop there. Let's take a quick look at the other questions. I think they're all sort of that ilk, yeah, I think that's pretty good. So if you have any specific questions, feel free to send me an email. And I'm not going to assign any new homework for today, just the same questions we did in yesterday's video. And also tomorrow's video will be on buffers. So I would really encourage you to maybe even read the section on buffers. I'm not going to go into too much detail as I do in the book, but if you're looking for a page to kind of read through, I would take a look at page 177 to 182. Okay, and I wouldn't worry too much about like understanding every single thing in there. It's fairly complicated, but I would say the buffers is probably the most complicated thing in this chapter, I would say. But they do tie in a lot to the titration curve, and also what we learned about V half. Although we apply that to indicators, the V half for an indicator, and determining its Ka value. But the buffers actually are done very similarly, but really important to understand that, where are we here? There's my pretty face. That the buffers are not really the same thing as an indicator. The indicator is used to determine the pH of a solution by showing you a color change. So you'll see a color change and you're like, oh, okay, I know the pH now is something to do with being more or less than this number, or maybe between two numbers now. Whereas the indicator, or the buffer, sorry, is a whole different kind of functionality, like why we would use them. If you've done biology 12, you probably know about buffers. And actually buffers are in lots of different things in terms of foods we eat, in terms of our bodies, and in terms of a lot of chemicals and things that we purchase, whether it's contact solution, even well, different things. We'll learn about that. But anyway, so what I would encourage you to do is read it first before you watch the video, because I think it is a hard concept to get your head around. But if you get your head around that, then the rest of the chapter is actually fairly straightforward, I think. So anyway, I'll say bye. Hope you guys are doing well, and we will see you, or you will see me tomorrow.